in the year 1944, there was a discovery which has had a profound influence on many areas of science and technology. This is the discovery of the phenomenon of magnetic resonance. This will be the topic of our discussion today. The phenomenon of magnetic resonance can take place both in the nuclear spin system as well as in the electron spin system of atoms and molecules. The phenomenon of nuclear magnetic resonance, for short it is called NMR, was discovered independently by two sets of people in 1944. One was Bloch, Hansen and Packard. The other set of people were Bloombergen, Purcell and Pound. Both sets were awarded the Nobel Prize in Physics for this great discovery. To understand the nature of this phenomenon, let us consider a sample containing a large number of nuclei such as protons in water. They have spin half, the simplest nuclear spin system. Whenever there is a spin angular momentum, there is a magnetic moment which is collinear with this spin angular momentum. If I is the spin angular momentum, so it is the nuclear spin, there is associated with this a magnetic dipolar moment mu. This is the magnetic dipole moment. And these two are parallel vectors, and the relation between them is mu is usually written in this form, mu equal to gamma h cross I. Here gamma is the nuclear magnetogyric ratio. Previously it used to be called the gyromagnetic ratio, but it is more appropriately called, it is the ratio of the magnetic moment to the gyroscopic angular momentum. So, it is magnetogyric ratio. H cross is h by 2 pi, where h is the Planck's constant. And this nuclear magnetogyric ratio has the value E by 2 m, where E is the nuclear charge, which in the case of proton it is just the electronic charge, and m is the nuclear mass. So, what we have is this set of protons in water is like an assembly of magnetic dipoles, small bar magnets or compass magnets. So, you have small dipole magnets to which we apply a uniform static magnetic field of strength B, which is directed along the z axis. The effect of this magnetic field is to line up all the magnetic dipoles. As we know, for example, if you have a compass needle, a mariner's compass, in the Earth's magnetic field, it always tends to line up along the magnetic north south direction. This is how mariners used to find direction in sea. So, this is a very well known matter of common experience. So, all the dipoles tend to line up along this z axis, and the energy of such a dipole, magnetic energy in a static magnetic field is minus mu dot B. This is again a well known result. So, if we use the value for mu from this, I can write this as minus gamma h cross I dot B, and since B is along the z direction, so this becomes minus gamma h cross I z B, where I z is the z component of the spin angular momentum, and we know that if m is the mi is the magnetic quantum number, then we know I z is quantized in units of mi. Mi has integral values. This in quantum mechanics is a standard well known result that mi is an integer, integral or half integral values going from minus I to plus I, 2I plus 1 values. So, because of this, this becomes where mi goes taking these integral values. So, corresponding to each value of mi, we have a different value of energy, and so these energy levels are called the Zeeman levels, which are shown in the figure. Now, the Zeeman levels are equally spaced. So, this is minus gamma h cross I into B, and this till gamma h cross I into B, 2I plus 1 levels. So, all of them are equally spaced, and the adjacent levels have a spacing equal to gamma h cross B. That is the energy difference between adjacent levels. These are the energy eigenvalues in a static field. And now, if a magnetic resonance takes place whenever in quantum systems, whenever you have a system with the different sets of stationary eigenstates, you couple them by inducing transitions using a perturbing energy Hamiltonian. So, here this perturbing Hamiltonian has to couple adjacent energy levels. So, this perturbing Hamiltonian or energy term is also magnetic in origin, therefore, we call it magnetic resonance. And this has to be a time dependent perturbation, so that the levels will be coupled. Otherwise, a stationary perturbation will not couple these adjacent levels. So, in order to induce transitions between these levels, you have to have a time dependent perturbation. In general, you apply an alternating or oscillating magnetic field. And by the same reasoning, the oscillating magnetic field, if I have B alternating e to the power I omega t, then this also has a coupling Hamiltonian, which is of the form mu dot B alternating e to the power I omega t. And therefore, if we want to couple adjacent levels, the only way there can be a non-zero transition probability between adjacent levels, you have to couple, because they have to induce transitions between some m value here, mi value state here, and an mi plus 1 state here, or vice versa. Therefore, you have to have a change in the magnetic quantum number delta mi should be plus or minus 1. So, the kind of Hamiltonian that will do this only something which involves the Ix or Iy. If you have Iz, it will not induce transitions among them. So, one must have an alternating field which is directed along the x or y directions. If the applied static field is along the z direction, static field, then the oscillating field has to be in the xy plane. So, this is the xy plane. So, the oscillating magnetic field should be directed in the xy plane perpendicular to the z axis. So, this is how a magnetic resonance transition is induced between the adjacent states. So, the figure shows this situation. So, for magnetic dipolar coupling, from this we can write this as minus gamma h cross I x or y e to the power I omega t b 0 b alternate, in which case the matching of the energy level should be such that this should be h nu or h cross omega. So, that is known as the resonance condition. So, this is the NMR resonance condition. Written in short, it will be gamma h cross b equals h cross omega or omega equal to gamma b, where b is the strength of the static magnetic field, omega is the angular frequency of the applied oscillating field. This is the strength of the static field. So, the resonance process involves an establishment of the Zeeman levels using an applied static magnetic field and inducing transitions among adjacent Zeeman levels by means of an applied alternating magnetic field of angular frequency omega. In other words, this can also be written as nu equal to gamma b by 2 pi, since omega is 2 pi nu. So, that gives the resonance condition. This resonance may be observed either by keeping the field constant and sweeping the frequency of the oscillator, or you can hold the frequency constant and sweep the field across the resonance. For protons, since gamma is a constant E by 2 m and this is 2 pi, so this can be calculated. The value is about 42 megahertz for an applied static field of B is 1 Tesla. Now, we are talking about time dependent perturbation inducing transitions between adjacent Zeeman levels. Now, what is the transition probability? Let us look at this a little closely. Transition probability for transitions between any two energy levels, say EA and EB. This is given by Fermi-Golden rule. Which has the form 2 pi by h cross A h prime B square delta h cross omega minus EA minus EB into, of course, density of states. So, this is a standard expression for transition probability P A B. Now, here this means this is the wave function of the state with energy level E A, and this is the state E B, and H prime is the perturbing Hamiltonian. So, this is the transition moment, the matrix element of the perturbing Hamiltonian between the two states, its modular square, and this ensures that this is a delta function which is 1 only when E A minus E B is equal to h cross omega. That ensures the resonance process, that when the energy difference is exactly matched by h cross omega, then there will be a non-zero value. Now, if you argue what is the probability of transition from reverse transition from B to A, that is also of the same form, because this is completely symmetrical between A and B. So, the transition probabilities both ways are the same. For an upward transition or a downward transition, the transition probabilities are the same. So, what is the number of transitions? The number of transitions is given by the transition probability times the number of atoms in a given state. So, if we are interested in the transitions, the number of transitions from level A to level B, then this is given by the transition probability P A to B times the number of atoms in level A. Similarly, the transition probability downward from level B to A is given by the same transition probability B to A times the number of atoms in the level B. So, the number of transitions will be equal if the number of atoms in the two states are the same. So, they will be non-zero, there will be a net preferential transition in one direction only if there are unequal populations in the two levels which are being coupled. Now, in thermal equilibrium, it is a standard result that if there are two energy levels with a level difference of this kind, then there will always be a population difference given by for any spin system in thermal equilibrium at a temperature T with a level difference delta E, then the lower level will have an excess population which will be given by this factor with respect to the upper level. So, it is this net population difference in thermal equilibrium which makes it possible to have more transition from the lower level to the upper level than from the upper level to the lower level. If there is more transition from the lower level to the upper level, then it will be absorption. So, because thermal equilibrium ensures that the lower level is more populated, there will be a net magnetic resonance absorption of energy at resonance. From the applied oscillating field. In a laser, for example, the upper level, the excited state is more preferentially populated in excess by what is known as a population inversion process, and therefore, there will be a laser emission, because the number of transitions from the upper to the lower level will be in excess. So, there will be an emission of light, and that is what we call laser emission. So, laser emission is just the reverse of magnetic resonance absorption. Now, a steady absorption, if we want, there will be an absorption. So, the spins will go from the lower level to the upper level, and eventually the two populations will get equalized, and then there is no excess population in the ground state, and therefore, there will be no absorption anymore. So, if you wait for some time, the absorption will die off. So, if you want to observe a steady absorption, this is possible only if excess population of the lower energy level is continuously maintained. At the thermal equilibrium value. In other words, when energy is absorbed by the spin system, which is in thermal equilibrium at a temperature T, and if the energy is absorbed from an external magnetic field, then this has the effect of heating up the nuclear spins. So, the temperature tends to rise. So, unless this heat energy, this energy which is absorbed is leaked away, so that it comes back again to the same original temperature and thermal equilibrium is maintained. In order to do this, this energy absorbed should be continuously leaking away to the external world. The spins are usually embedded in a crystal lattice. For example, the protons in water are inside the bulk of the water, which serves as a thermal bath. So, the water absorbs this energy absorbed by a process. This process of leaking away energy is called a relaxation process known as spin lattice relaxation. The external bath, which acts as a heat reservoir which absorbs all the heat which goes into the spin system, that is called collectively as lattice. So, the bulk of the water is the lattice in this case. This is because in a crystal, solid crystal, this is a lattice. So, because of that, that term has stuck. So, there is a relaxation of the spins through the coupling between the spins and the lattice, and this relaxation means it is as if you are heating up a system, a rod is being heated up, and the rod, it is also radiating away this heat to the external world. So, it is similar to that. The spin system is in a temperature T, and then it is connected thermally to the outside lattice, and there is a connection, there is a thermal connection between the spin system and the lattice system, and there is a time taken for this heat to be leaked away. So, it is called a relaxation process. It is the spin lattice relaxation which ensures that the energy absorbed by the spins is continuously transferred on to the heat bath, namely the bulk of water or the crystal lattice, which acts as a thermal reservoir, so that thermal equilibrium is maintained at the temperature of the nuclear spins. So, this is necessary in order for a steady absorption to take place. So, the resonant process is illustrated in the next figure, where you have what is shown is a magnet which produces a static field. The north south direction shows the lines of force, and then you have a sample inside it, that is called the probe here, and then there is a high frequency antenna which couples the alternating magnetic field to this spin system, and you can sweep either the magnetic field or the frequency of the oscillator, so that the resonance takes place, and the resonance absorption from the oscillator is coupled as a signal into an amplifier and then displayed. So, that is the basic schematic of the resonant process. The experimental arrangement is shown in the next figure, which is of course a little more detailed, and that is the way it is seen in any laboratory with an NMR spectrometer. Now, this is all quantum mechanics. One might ask, is there no way of understanding this process? Resonance is known classically, magnetic field, electrodynamics, magnetic field and its interaction with nuclear angular momentum, all these are classical ideas. So, why should we have a quantum mechanical explanation? The answer is the resonance can be explained classically, and the way to explain this is via the torque exerted by a magnetic field. If I have a magnetic moment, a dipole moment mu, then if I have a field acting on it, then there is a torque. It is a well known result of classical electrodynamics that the torque is mu cross B. Now, by torque equation, which is just the analog of the Newton's equation for the force and the momentum, rate of change of linear momentum, the torque is connected to the rate of change of the angular momentum. So, it is di by dt. This is just the analog of the Newton's equation, F equal to dp by dt. So, instead of F, you have the torque here for a rotational motion, and then instead of the linear momentum, we have a spin angular momentum. So, this is the torque equation. So, now substituting for mu, I can write this as gamma h cross I cross B. Now, in order to make this understand the physical content of this torque equation, let us just go over from a static reference frame of coordinates, system of coordinates, to a rotating frame. And classical mechanics tells us that the rate of change of any vector when viewed from a rotating frame which has an angular frequency omega is related to the rate of change in space fixed coordinate system plus omega cross I. This is a standard result in classical mechanics. So, let us apply this to this situation and get this as gamma h cross I cross B plus omega cross I. I can bring it together by writing gamma h cross B minus omega cross I or minus. So, this time rate of change will become 0 if the resonance condition, namely omega equal to gamma h cross b, is satisfied. So, this is again the resonance condition. So, we have classically the result that if you go to a rotating frame which is rotating with an angular frequency which is equal to the resonant frequency, then again we will have a resonance process in which energy is absorbed from the oscillating magnetic field by the nuclear spin system. So, this phenomenon, because the angular momentum is fixed, because its time rate of change is 0, that is a fixed vector in space, and that is the phenomenon which is known as precession. We know this from the motion of a top or a gyroscope in classical mechanics. So, this is gyroscopic precession. Which was first recognized by a person called Nmr. So, this is known as Nmr precession. So, the angular momentum is preserved, the spin is precessing about the direction of the applied static field with an angular frequency equal to the resonance frequency. So, the resonance frequency is nothing but the Nmr precession frequency. So, this precession is shown in the next figure. So, you have the applied magnetic field and then the precession takes place about this field direction. So, the resonance condition gives the frequency at which magnetic resonance absorption takes place, and the intensity of absorption is governed by, again as I discussed already, the population excess of the ground state by vis-a-vis the excited states. Now, this excess of population is given by the Boltzmann factor. Population excess. In ground state is given by the Boltzmann factor exponential minus delta E by kBT. This explains why, for example, if you take the electrons and the nuclei, we can also have a similar consideration of electron resonance as well. Now, the magnetogyric ratio is E by 2m in the case of the electron, while for protons it is E by 2 capital M, where M is some 2000 times, 1873 times the mass of the electron, and therefore, the proton magnetic moment is that much weaker, a factor of 1000 weaker, and therefore, the energy levels are smaller, whereas here the energy levels are much higher. So, 1000 times larger. Therefore, we already saw for a 1 Tesla field, the nuclear resonance for protons in water takes place around 42 megahertz, whereas the corresponding frequency for electron spin resonance will be in the gigahertz range or the microwave region of the electromagnetic spectrum for electrons. Usually in the X band. So, for electron resonance to be observed, sample again should have unpaired electrons carrying a net angular momentum. We already discussed this situation in connection with electron magnetism. So, for example, paramagnetic ions. Or free radicals and so on, crystal defects. So, that next figure shows a typical electron spin resonance spectrometer. The components are self explanatory, they are standard microwave gear and techniques for observing the resonance and so on. So, if we have a macroscopic sample, we wrote all these equations were written for a single dipole, but if we have a macroscopic sample containing some 10 to the power 24 spins, then we have to change the discussion to the magnetization M. It is the case of the magnetization vector, which is the resultant of all the spins, that has to be discussed. So, it is the precession of the magnetization vector, and this precesses at a rate which is determined by the spin lattice relaxation time, etc. Therefore, we can write the time rate of change of the magnetization vector as follows. So, we will write the time rate of change for the different components of the magnetization. This will be by the torque equation, the z component of the cross product, and then minus. So, this is the time rate of change according to the spin lattice relaxation time, and similar equation for dmx, the transverse magnetization component, mx or y. Now, the transverse magnetization, the decay of the transverse magnetization is governed by a different spin time constant. So, T1 is known as the spin lattice relaxation time, as explained already. It gives the decay of the z component of the magnetization and its evolution to go into the steady state value of the magnetization. The steady state equilibrium magnetization is established in a time of the order of the spin lattice relaxation time, while the transverse magnetization is decays at a rate which is governed by the energy exchange among the spins. So, it is called the spin-spin relaxation. In this form, these equations are known as the block equations. Which describe the resonance process. Solution of these equations in any given situation leads to a precessing magnetization in the xy plane, which decays with a characteristic time constant T2. And if there is a precessing transverse magnetization component, if you wind a pickup coil around the sample, one can measure the induced EMF via Faraday law, which is at the resonance frequency. So, this is the phenomenon known as nuclear induction. Even though magnetic resonance occurs usually at the resonance field value, which is given by the resonance frequency as discussed already, we may be thinking that we are applying a resonance field, but there may be additional internal local fields due to interactions among spins, and these fields can be of different origins. Now, if such a field exists, a local field, an internal field, then the resonance is shifted by an amount equal to the local field. For example, in a liquid sample, this shift is known as chemical shift, and one can look at high resolution, it is called high resolution NMR, which can serve as a sensitive probe to determine the chemical environment of the nuclear spins. for example, a typical NMR spectrum of protons in ethyl alcohol is shown here. In ethyl alcohol, you have CH3 and CH2 and OH. All these contain protons, and so there are 3 different resonance peaks because each of these have a slightly different chemical environment. So, there is a shift due to these internal fields, and so you get 3 sets of NMR resonance peaks. I do not want to go into the details of the additional structure which you see there and so on. So, you can get a lot of information about the chemical environment, and then you have the intensity ratios can tell you about how many protons are there. For example, you have CH3, so you have a much larger intensity and so on, depending on the number of protons, 3 protons in CH3, 2 in CH2 and 1 in OH. So, correspondingly there will be intensity differences. So, the ratio will be 3:2:1. So, by measuring the relative intensities, one can get also information about the relative concentration in a given molecule. So, the relevant parameter in chemical shift is called delta, representing the fractional deviation measured in parts per million. As I told you, it is a high resolution NMR. So, the changes are in parts per million from that of a standard sample known as, usually this is a compound known as tetramethylsilane. It is known short as TMS. So, it is a convenient standard which has a reference value, the chemical shift is 0. So, a small amount of TMS is always added to the sample, so that it calibrates the chemical shift measured. And as I already told you, with higher resolution it is possible to identify further splitting of the chemically shifted peaks due to spin-spin interaction. Well, I do not want to go into all these details now. Similarly, another similar situation occurs in the case of a hydrated crystal. Now, in a hydrated crystal you have water molecule. So, you have 2 protons in a water molecule. So, because there is an interaction between these 2 protons, there is a dipole-dipole interaction which causes the NMR line to split into 2, whereas normally you expect a single resonance peak like this. This splits into 2. So, that would be the nature of the absorption which you observe, and this, as you change the direction of the angular magnetic field, the direction of the interproton vector is changed, and so you have an angular variation of the splitting. Of dipolar splitting. Since it is dipolar splitting, this angular variation can be shown to have the form 3 cos square theta minus 1. So, by measuring this angular variation, one can measure the orientation of the interproton vector inside the crystal, and the splitting is proportional to mu by r cube. This is the dipolar field, where r is the distance between the 2 protons. So, one can measure the length and orientation of the interproton vector from this angular variation, and this, when coupled with additional crystallographic information from structural data, one can even locate the positions of the protons. This is, as we already discussed, this is a rather difficult problem. The location of light atoms positions such as protons is normally difficult in X-ray diffraction studies. Usually neutron diffraction is necessary in order to do this, and neutron diffraction is not an experiment which is easily available to everyone. So, NMR provides an alternative way of determining the position of hydrogen atoms in solids. Now, this dipolar splitting is determined under the assumption that these spins, the 2 protons, are staying fixed, but at any finite temperature in a liquid, for example, there is a rapid movement of atoms and molecules which causes an averaging out of these local fields, and therefore, the resonance field will be narrowed. So, it is known as the narrowing due to motional narrowing. So, this motional processes also can be studied using such variations. Now, let us spend a little time looking at electron resonance. In the case of electrons, we can have very similar considerations for the observation of an electron resonance, because the electrons in an unpaired electron spin system or have a net angular momentum. So, the resonance process is very similar, except that it is shifted out to microwave frequencies for the same fields. But again, just like the dipolar splitting due to internal fields, similarly the electrons interact with nuclei. The electrons and nuclear spins interact via what is known as the hyperfine interaction. So, electron nuclear interactions. They are of two kinds: hyperfine interactions, magnetic hyperfine interaction, and electric quadrupole interactions. We will not go into all these, but when an electron and nuclear spin interact via the hyperfine interaction, it will again change the local magnetic field, and so the resonance frequency will be shifted. Now, the hyperfine interaction due to s electrons, which have an isotropic angular distribution, is isotropic. It does not have an angular variation. This part is known as Fermi contact interaction, hyperfine interaction. Then you have p electrons and d electrons, which have an anisotropic hyperfine interaction. Both these can be investigated using electron resonance as well as nuclear resonance. In addition, in metals, we have conduction electrons. So, the conduction electrons again interact, giving rise to a local field, and this produces a shift in the NMR, which is known by the term night shift. So, by measuring the night shift, this can again tell you about the conduction electron spin densities. Now, you can also have, because of the electron nuclear coupling, you can polarize the electron spin system or magnetize, if you like, via the nuclei, because there is a coupling between the two systems, they are interacting. So, and as we already saw, it is much easier to observe electron resonance than nuclear resonance, because the energy level differences are much higher. So, the intensities are much stronger here. So, if you can transverse the nuclear polarization to the electronic system, then you can observe the nuclear transitions via the electron resonance, that is known as a double resonance technique. In this case, it is known as electron nuclear double resonance, ENDOR, ENDOR. So, the double resonance technique is of great interest, because you can use the sensitivity of the electron spin system and measure a relatively weak spin signal which occurs in the nuclear system via the electron coupling. Now, looking at the electron spin resonance process a little bit closer detail, in order to do this we should start with the Hamiltonian of an electron. Of a mini electron atom, say. The Hamiltonian is sigma pi square by 2m. This is the kinetic energy of the electrons summed over all the electrons labeled with the index I. Then we have the Coulomb attraction between the nucleus and the electron. So, both are the kinetic energy, this is the Coulomb potential energy of the electron in the presence of the nucleus. Then you have many electrons, so you have inter-electron repulsion. I write I less than j because we do not want to count twice. This way we write R12, but we do not write R21. So, R12 and R21 are the same interaction. So, we do not want to count them twice. So, this is a summation over all such pairs of interactions. So, this is the inter-electron repulsion. Then we have the spin orbit coupling. This is the coupling between the electronic spin and orbital angular momentum. Then we have, this is actually a resultant of then we have the Zeeman field. Depending on how strong or weak the magnetic field is relative to the other interactions here. So, this will give you the different terms which are involved in the Hamiltonian in descending order of energy, and then sometimes the spin orbit coupling will be weak in comparison to the Zeeman coupling. In other cases, the spin orbit coupling will be strong in comparison to the Zeeman term. So, depending on that, we have to consider the Zeeman term and its effect on the nuclear electron spin system appropriately. So, this will again give you the resonance condition in the form this is the resonance condition, where Gj is the Landé G factor. We have considered these already in magnetism. So, that would be the electron spin resonance condition, and the electron spin resonance transitions are shown in schematically in the figure, where you have a field and the Zeeman splitting, which is linear, splits this as the field is increased, and then transitions are induced between the two Zeeman levels, adjacent Zeeman levels, via an oscillating field. So, the G factor is determined by a perturbation of the so called ground multiplied by the crystalline electric field of neighboring ligands, as we discussed already, such as O2 minus, sulfate, and so on. So, the effect of the crystal field is something which we have already discussed, and therefore, the G tensor is a second rank G tensor, a second rank tensor, which reflects the symmetry of the crystalline environment around the paramagnetic ion. So, it is as if you have a microscope to look at the internal crystalline environment. In complexes of transition metal ions, the delocalization of the electrons, we already discussed covalency. This delocalization determines the degree of covalency and causes a deviation of the G value from the free ion value. And further splitting of the electron resonance line, as we already discussed, is produced by hyperfine interactions. So, the general analysis of the angular variation of the electron resonance spectrum can lead to the determination of the isotropic part of the hyperfine coupling as well as the principal components of the hyperfine tensor. This is also the case with electric quadrupole interactions in the presence of a crystalline electric field gradient. And when there is covalency, this can also produce so called super hyperfine structure due to the interaction between the electronic charge distribution and the nuclear spin of a neighboring atom or molecule. So, that is called super hyperfine interaction. We already discussed how motional narrowing can affect the NMR profile. Now, we discuss exchange interactions between electron spins, and that can produce a similar narrowing of the electron resonance line width. So, this is known as exchange narrowing. So, thus it is clear that NMR and ESR studies of condensed matter systems can provide a wealth of information regarding the structure, the symmetry, the distribution of internal magnetic fields due to different types of interactions and the various rate processes. Now, I should mention medical applications. For example, the magnetic resonance imaging MRI has also rendered magnetic resonance as an important modern diagnostic tool. Well, that magnetic resonance can provide a very high resolution probe into condensed matter.